Kristen Hunter-Thompson and Annette Brickley. We're working to bring specific data moves, data strategies into these resources to help students talk about the data, identify and describe visual patterns before we get into the analysis part of the work that we're doing. So their work's been instrumental here, and then also just recognizing that serious scientists have been obviously important in the work, but it's the science teachers that I've gotten to work with, of which I think we're up over 500 now teachers that have attended webinars and professional development events, and their continued emails, showing up, contributions have helped me refine these resources and make them what they are. So there are many more people than this team, but want to acknowledge them and then acknowledge the different data science work that's been done before me. Many of you have probably heard of data nuggets. I've created some of those lessons with folks at Michigan State who do that work. We've kind of put our own spin on it with these data puzzles. FET at CU Boulder and some earth science puzzles. Again, we're trying to build on the backs of others that have come before us. The story of this resource started in 2019 with the Mosaic expedition. I was telling Evan about this morning. It's one of the largest expeditions ever conducted to study the changing Arctic climate system. Get to use the laser here. In 2019, let's see, a group of about 100 scientists hopped aboard the Polarstern, a German icebreaker, and set sail into the central Arctic to find an ice floe, a flat piece of ice with which to freeze itself into. And then the scientists aboard that Polarstern, that icebreaker, deployed hundreds of instruments up to 50 kilometers away from that drifting observatory. They drifted with the sea ice across the Arctic for an entire year, again, to understand all aspects of the climate system, with the goal of refining models for the Arctic climate system so we could create more robust climate models for the entire globe. So I was hired to do this outreach, and we developed quite a following of educators nationally and globally because this was such an international, well-funded effort. In fact, I just received an email yesterday from a teacher I've worked with for a number of years, and I thought, I don't know, I just wanted to share it. It moved me and made me feel like I'm making an impact, and I think in these times, like finding these little moments of inspiration is important. So didn't want to get political, but whoa, the news stories about Greenland's ice sheet and resources up there, making a certain president want to acquire Greenland. I'm proud of the work that we have done with Mosaic curriculum, making me think of different changes that I might make to next year. Anyway, thanks for making a great curriculum. And I think that, I don't know, for me, this is inspiring and motivation to keep doing what I'm doing, and I hope that scientists like yourself continue to work with Becky, myself, or other community members to bring your research out into the public. So I was grateful to get to work with this teacher, grateful for my experience with Mosaic, grateful for that following, and grateful for what has come from that, which is teachers wanted to continue working with Arctic data as a result of their exposure to the Mosaic expedition. And we wanted to provide that to them in a new structure, in a new form. So using our resources, Melissa Bratton and my experience in the classroom implementing ambitious science teaching practices, we combined the two to create data puzzles. And so what we've done with data puzzles is take this ambitious science teaching framework. This is a textbook that has strategies and practices and describes how you could do things in the classroom, and we've tried to take that framework and actually put it into a structured lesson. Teachers are busy and they don't really have time to write their own curriculum. Yes, these strategies are important, and yes, we want them to use them in their classroom, but I think it's helpful for sometimes to see an example of what is a resource that uses these practices. And so with permission from the folks that wrote the Ambitious Science Teaching book, we've reworked their framework, their structure, into this data puzzles framework. So all of our data puzzle resources follow this same structure. We start by meeting students where they're at. We want to elicit student ideas through an opening scenario that's going to have similar science ideas to an investigation they'll later connect with. So if we're talking about the Arctic, perhaps a middle school student hasn't thought much about the Arctic, but knows that when they go outside on a snowy day, it's really bright. So asking a student at the forefront, like, why would this person want to wear sunglasses today? Or if you've ever been skiing, like, why do you get so sunburned on a sunny day on the slopes? Getting students to talk about those experiences. Perhaps the word albedo comes out, maybe it doesn't. But trying to have those discussions where we are eliciting student ideas, experiences as language, that's the starting point. That's the way in which they make sense of the world. And we as educators, we want to know that starting point so that we can build on it. We can use those experiences to help them make connections to new investigations or new experiences. So after we've revealed these resources in the opening scenario, that's when we would introduce a science investigation like any of you might be investigating. And so we do that through an interactive text called a puzzle plot. Students read this puzzle plot largely through whole class readings, and then we challenge them to make connections between their own lived experience and the text. The text might have some virtual field trips or some videos as well. Students are asked to make some initial models about questions that are presented in the puzzle plot text, make predictions based on their lived experience or things that they've read in the text. And then they test their predictions by analyzing a data set in this supporting ongoing changes in thinking. The final piece of the puzzle, so to speak, is to bring all of this together into a final evidence-based explanation for a question about a phenomena that's introduced in this puzzle plot text. And so these evidence-based explanations also often take the form of an annotated sketch. And so what I want to do here today is kind of collaboratively engage with these different quadrants in the context of one of our resources that's called the tipping point. So you'll hopefully get a feel for the different quadrants and how they fit together to help students connect to the science and tell a story. Diving into this first quadrant here, eliciting student ideas, the goal here is to bring out resources that students have that are related to the science investigation that will be presented later in the data puzzle lesson. So again, before dropping students off in a tropical forest or in the Arctic, like what connections can they make in their everyday life that have similarities to the things that the scientists are studying in those spaces? And teachers have done this with warm-up prompts where students come in, they sit down and maybe jot down an answer to a question on the board in their science notebooks, or a think, pair, share, talking to their neighbor. We've had other teachers like to do this with whiteboards, and then students share their ideas. And I think, Evan, I just keep coming back to our conversation this morning in which you asked me, like, what do you think is causing tree mortality in the tropical forest? And I'm going to flip it back on you all. I was going to do that same thing here. When I'm facilitating professional learning experiences for teachers, we often challenge them to get in the side of the head of their students. What would your students say to this question so you can anticipate where you might be going? So I'm going to ask you all to think as if you're a 12-year-old. Put your 12-year-old hats on. This is called student hat. And kind of popcorn style here, all the 12-year-olds in this audience, every time you go to the doctor, you get your vital signs measured, things like heart rate, blood pressure, body temperature. Why? Why do these doctors care about your body? You might not even be feeling sick, but they still take your temperature. Why do they want to keep track of these vital signs year after year? This is a teaching strategy too called wait time. We'll just wait. We'll wait it out. Yeah, Evan, what do you think?
To know if you're staying the same.
They're knowing if they're staying the same. Okay. Yeah, Shannon.
What
Yeah, yeah. That is typical. That's why I go to the doctors, make sure I don't die before I leave that building. Yeah.
Mine is similarly with my 12-year-old hat on. To make sure your heart's not pumping so much it's going to explode.
Yeah. You wouldn't want that to happen. Yeah.
We have a contribution from online because they have to for the insurance.
Ooh. Wow, that's a 12-year-old that's taking care of insurance claims. Right, so we're trying to get out, it's fun to be playful. I mean, 12-year-olds are going to be playful, so experiencing this too, you know, they do it every time. My temperature was this last time. My temperature was this. My temperature is always this. Or my blood, I don't know if they're going to share those things, but the importance of establishing a baseline so we can monitor changes to see if you're sick, you're healthy, if your heart's about to explode. We want to establish that baseline. We would then ask the question, okay, well, humans go to the doctors to track their vital signs, to identify changes and potential problems. Imagine if you could take a plant to the doctor. What kind of measurements do you think the doctors would want to take? And how might the doctor know if the plant was unhealthy? So when we pose this to students, they might say, you know, from their own lived experience, the color might tell you something about the health of the plant. Or, you know, if I'm thinking about my 3-year-old daughter, she's drowning our plants every day. She loves watering the plants. It's like, well, that's maybe a little too much, but or picking them off, or, you know, so temperature, water, color. Students come up with all sorts of ideas. Like they have experience with this. And they're able to monitor those things and establish a baseline. Changes to those things might tell you whether a plant is healthy or unhealthy. So hopefully we can make connections to their lived experience in the doctor's office, their lived experience with plant, the importance of baseline, changes to those baseline. And then we use this opening scenario as a way in to introduce these students to plant doctors, ecologists, plant ecologists, like many of you are. Doctors Dan Doak from the University of Colorado Boulder, Megan DeMarsh from the University of Georgia, Bill Morris from Duke. They've been working on LTER sites across the western United States for 20 plus years. And they're particularly interested in a particular plant called moss campion. They've been measuring vital rates, survival, growth, reproduction rates, and how these vital rates have been changed by changes in their environmental condition. So we have data from these scientists, these plant doctors, more than 20 years of data, and they hope to continue this work for 20 more years. So through this opening scenario and through this eliciting of student ideas, hopefully you can see how we've taken students' lived experience. We've navigated through that to get and segued that to introduce the scientists, and then let's go learn a little bit more about these scientists in this puzzle plot text. And so the goal here again is we're trying to make some sense of the work these scientists are conducting related to moss campion plants, have students make connections between the opening scenario, which you just experienced, and this text. There are some questions that ask students to summarize key ideas, make annotated sketches, which act as these initial models, and then make predictions about questions that are being presented in the text. I'm reminded now of conversation I had with Shannon this morning. This is one opportunity, like the sense making that Becky referred to. We need to establish where students are in terms of their understanding of the world around them, and then we need to provide opportunities for students to wrestle with what they know or what they think they know, and new experiences, new topics. So when we're having students make predictions or make models, right, they're projecting their views, their understanding of the world, and applying it to new situations. And throughout data puzzles, we're trying to give students multiple opportunities to wrestle with new ideas, to make sense of the world around them. So these initial models, these predictions are opportunities for them to share what they already know and apply them into new situations. We ask students to read this text, circle investigative questions, underline similarities between that opening scenario and this new investigation, and then offer in teacher guides some different teaching tips and key points that we want teachers and students to leave this part of the lesson with. We're not going to have you read that today, but just wanted to point out a few things, a few important parts of this work that's highlighted in the text. Moss campion, shown over there on the right. It's an alpine tundra plant, a cushion plant. It grows across a vast latitudinal range. These are the data that we'll look at here in a moment. Data that was collected from 4 different field sites here, ranging from New Mexico all the way up into northern Alaska. It's a nursery plant, provides important habitat for other organisms that grow in and around that cushion plant. And these scientists, as was mentioned, are investigating the vital signs to see how the plant is responding to different environmental conditions. So students are introduced to that plant and then asked and presented with this. These are pictures from Dr. Megan DeMarsh, who's featured in the lesson. You can see the same moss campion plant across 3 different years. Little hard to see the fruits on this first plant. You can see them here. And these scientists measure the production of these fruits as a measure of their reproduction rate. So you can see in 2003 there were 4 fruits. I can only locate 1, right? I guess 2. Megan tells me there were 4. 18 in 2004 and 0 in 2005. So we're trying to think about what could be affecting moss campion reproduction. So what is going on that's causing reproduction rates to be higher or lower? Again, this would be an opportunity for you to ask students to share through their lived experience. We've kind of prompted them with that question about what would you measure if you were a plant scientist to determine whether it's healthy or unhealthy. What could these scientists measure to investigate these differences in reproduction rate? And so again, we'd expect students to say things like temperature, precipitation. A lot of students are thinking about pests or organisms that might be coming and eating the plant, harsh winters. The list runs the gamut. And so a lot of times what I'll do is make note of all these ideas and create public records so we can refer back to these ideas throughout. So students, again, an opportunity to make another prediction here, what's affecting moss campion reproduction, and then that's how we make our way into part 3 here, supporting ongoing changes in thinking, where we're going to test that prediction by looking at some data collected by Bill, Dan, and Megan. A key point here from Melissa Bratton, the author of Ambitious Science Teaching. It's so important to talk about the graphs before challenging students to analyze them or identify patterns. We have decades of experience analyzing data, asking questions of data, looking for patterns, noticing different features that students do not have. And so what we're doing with data puzzles is including specific teacher moves, specific strategies that challenge students to make moves that we want them to make, right? So we want to give students practice with data moves in these structured lessons, so then they might be able to enact them on their own in more open-ended investigations. Talking about the graphs, I'm gonna show you what the slow reveal strategy is and how it shows up in this lesson. And then once students have talked about the graphs, there are a series of data analysis questions that they can answer on their own or with a partner. And so what we're going to do now, we're going to look at, this is the data set. We're testing our predictions, what could be affecting moss campion reproduction. We're asking students, you can take a moment to think about it. What do you notice? What do you wonder? Often when I present this to scientists, they're frustrated. There's no X and Y axis. That's what I notice first. What I wonder is, what is the X and Y axis? We're going to have to move beyond that. Things we're noticing, there are blue bars. They're different heights. really small bars on the left. They go a little bigger to the right. Okay, I'm wondering what the axes are. Okay. What did we just learn? Did that change our thinking? So we've presented this with teachers and students. Now they're thinking, we've got reproduction rate, number of fruits per year, per centimeter square. That's kind of a cumbersome unit, but okay, we'll take it. And thinking back to the factors that I think might impact moss campion reproduction rates. I don't see that here yet, so I'm starting to speculate what that could be on the x-axis. I kind of thought it was going to be time. Maybe it's not time, so we're kind of grappling with this, trying to slow it down. Okay. New information did we just learn? So now we've got average July temperature on the x-axis, reproduction rates. So we're starting to, so now we're taking those predictions. We have lots of different variables, environmental factors that could be impacting reproduction rate. We're keying in now on average July temperature. Perhaps some different questions are emerging as you're looking at this, like why average July temperature? There's a lot of, what about the rest of the year temperature? What other factors besides July temperature? Those are all things that we've had teachers share with us. One thing that's missing here, I'm going to ask you again in your head, make a prediction. We're missing this last bar over here in the 16 to 17.9 temperature zone. And based on what you see here, what might you predict the reproduction rate is going to be over there? Perhaps because of the name of the lesson, the tipping point. Maybe that kind of gives you a hint. Maybe not for students. But we can see here that reproduction rates for moss campion plants, based on this data set, seem to increase with increasing temperatures up to a certain point, tipping point, beyond which reproduction rates decline dramatically. So the purpose of this slow reveal strategy is to really get students to focus in to talk about it, but I really wanted students to describe this particular visual pattern. I want students to see this curve, this tipping point. Had I just thrown this graph on the screen for students, maybe some of them will see it, but by slowing it down, getting students to talk about it, make another prediction. Here, we've had success in terms of students being able to articulate this and then answer questions on their student worksheets, construct models to represent these data visually. So again, this slow reveal strategy is kind of increasing in popularity. I'm not sure there's been a lot of educational research on it, but I know anecdotally teachers across the country are using this more and more. In this case, again, the shape of the graph was critical, so using this particular strategy, wanted to show, wanted students to see that reproduction rates were increasing, but at some point decline and make sense of why that could be happening. So describing visual patterns is a key data sense-making practice, and this strategy helps students get there. After students have analyzed this data, we've talked about the data, the final piece of the puzzle is for students to take those new understandings and construct an explanatory model for the question, what's going on with these reproduction rates, what's causing reproduction rates to change. For this, looking at some student work, right? Pretty simple, but for students, can be challenging to take what they see on a bar graph and make sense of that visually and explain what's going on. So these are some student examples, some 8th grade students using the key moss campion seeds, moss campion fruits, We've got different temperatures, and so different reproduction rates as represented by seed. Where we're trying to get students to is to really include data from graphs into data visualizations. So again, these sorts of explanatory models, these annotated sketches, are really becoming widely used in classrooms across the country. And so we are trying to support teachers and students in this particular type of resource, structuring that for them so they can be successful. The final piece here is for students to consider what questions they should investigate next, and Bill, Dan, and Megan, hopefully that funding that they received in 2024 for 5 more years of research stays true. But for students and for you all, like I'm sure there are lots of questions about that graph that was presented to you about that research. We didn't present all aspects of their research. So what questions do you still have about moss campion, and what do you think these scientists should investigate next? The reason we're doing this is because we're planting the seed for the next activity, this open-ended data investigation, the puzzle piece. And so students engaging with this, teachers, they're using their critical thinking skills, applying like things that they were maybe frustrated with when they're engaging with the lesson, like they want to know more about. This is their opportunity. Create those questions. So the recap here, we've elicited our ideas, talked about why these baseline conditions are important, how you could monitor the health of a plant. We've learned more about a particular plant, moss campion, and how these scientists have investigated the vital signs of this plant over 20 years. We've looked at a data set that's taken moss campion reproduction rate data from these 4 sites over the 20-year period, and we've seen that there's this tipping point. And then ask students to construct a visual representation of that tipping point, making sense of it through an explanatory model. So a lot of sophisticated moves that we're asking students to do that might seem simple to us, but fairly new to students in their classroom, where they're having to do the thinking. They're wrestling with new ideas through the context of what they already know or have already experienced. Students are left with more questions, right? That's kind of why we end with that digging deeper part. What could you investigate next? We've tested these out in classrooms so we can kind of anticipate what they've would want to know more about. And then we've curated additional data sets that are larger and messier that might allow them to investigate those questions further on their own. So in this particular lesson that you just saw, we've got data from 4 locations, 3 states, 20 years of data. We're looking at July temperature and reproduction rates. And here's an example of 9th grade students from a high school in Massachusetts. Here are some questions that they came up with after engaging with that data puzzle lesson. Temperatures that might lead to no reproduction. Students were really interested in these antifreeze proteins that was mentioned in the puzzle plot text. There was talk in this classroom about precipitation and the importance of snow before they developed these questions. So lots of questions about snow and how that might impact reproduction rates. This particular class had done some work with bees too, so thinking about flowering and the importance of flowers and reproduction, bees. So starting to make some different connections, moisture really standing out here. And it was at this point with students, and what I'll introduce to you now, this is a new resource for us that hasn't really been classroom tested, but we're excited about this open-ended data exploration piece through these puzzle pieces. So these are going to include ingredients of the structured lesson that we just went through, but in a format that offers students and their teachers an opportunity to play with data. So CodeApp is the name of this tool. It's an NSF-funded initiative to be able to bring in data sets into this free platform and play around with it. In these puzzle pieces, not only is there a CodeApp window to play with a data set, but there's some context behind the data set and strategies to connect the data set. to existing data puzzle lessons. So strategies to connect open-endedness to the structured lesson. These are teacher-facing, so while this right here is student-facing, which means you could give it to a student and collaboratively work through the resource, the puzzle pieces are teacher-facing, so teachers would need to take that information and create their own lessons to bring them into classroom. That's what it looks like in its current form. And so I'm going to take you there in just a moment, but this new data set that we'll check out is only from one state, the Niwot, it's from Colorado, the Niwot Ridge LTER site. 5 years of data from 600 tagged plants. We've got some reproduction rate data, but also some additional data sets, temperature, snow melt to kind of get at the moisture questions that students have had, and then day of first flower. And so we introduced these new environmental factors and variables to students through the development of a timeline activity to get students thinking about when the snow melted in the Rockies, when flowers tend to bloom on these moss campion plants, and then take students to the field site through virtual field trips, something that we're doing a lot more with serious scientists, sending them out with cameras to capture 360 images. And then we work with them to build 360 tours to actually bring students to the site so they can see the instruments and scientists collecting the data before they are asked to play around with the different data sets. So after introducing students to these variables and their field sites, that's when we'll take them to this CodeApp product. And I'm going to exit and take you there myself. This is what a puzzle piece looks like. So I know it's a little small up there. Sorry about that. But there's some context, how to explore the data. There's an embedded CodeApp tool where we'll show you how to drag and drop different variables from this table to build your own graphs and play with data visualizations. Matt told me that this was kind of fun to show off this virtual field trip. So we can take you to Niwot Ridge and click and drag and see these different images, icons to look at text. Where should we? We've got videos, photos to show students and teachers, folks doing that work. So again, these are all kind of supplemental materials to introduce students to that site, some data collection methods. And then the CodeApp tool looks like this. I've worked with some scientists from Earth Lab at CU Boulder, and they've enjoyed this. And so also different professors on campus are starting to bring this into their classroom. So we can do things like the students were excited to learn more about first day of flower. So we dragged a variable over and we could see, kind of using that same slow reveal teacher move, we can build these graphs slowly. We could see how snow melt might impact that. Okay, so we can see snow melt impacts first flower. We can add some trend lines to this. Some other interesting applications of this tool, lat long coordinates. There are 4 sites at this Niwot Ridge location. We can look at where those sites are on a map. So there are 4 sites. I can do things like sites 1, 2, 3, and 4 are labeled here. I can drag them over the top. I'm going to get rid of all of those trend lines. That's a lot to look at. But I could look at things by site. Looks like this site here, blue, the snow seems to melt a little bit later. Flowers seem to be a little bit later too. So there's lots of applications here. And what we do with students is we have them just play around. You create multiple maps. You're interested in snow melt? Okay. How does snow melt affect reproduction rate? Okay, that's interesting as well. So what questions might students come up with? How does snow melt impact reproduction. We know July temperatures impact reproduction rate from the previous data set, looking at snow melt. We can look at these conditions broadly. We can look at how individual sites are reacting or responding to environmental conditions. So one thing that we encourage teachers and students to do is to wrestle with, use this question, the question board that they create, as a way to organize the exploration using CODAP. So if we're thinking about day of snowmelt reproduction rate, what was the question here? Are there differences in reproduction rate early versus late snowmelt? So challenging students to think about which variables, which attributes they could pull over into that CODAP table that might answer that question. Then we have students in small groups share what they've done, share what they've learned, and then share out as a whole class. So it's really a fun opportunity for students to kind of show off, to share what they've learned, to drive their learning. And hopefully that thinking is guided by the way in which different environmental factors are connected to the health of the plant or the phenology of the plant. Another thing that stood out for students in this Massachusetts class, understandably, what they know about moss campion. When the snow melts earlier, the flowers tend to bloom earlier because there isn't that snow covering. They can start that process. I think the students really enjoyed this. They had more questions than the data set could address. They were particularly interested in bees, having just finished a bee unit, and the mismatch or potential mismatch of when the flowers bloomed and when the bees might arrive. And so we were excited about the application and the ways in which students were able to take questions from the structured lesson and investigate them in this more open-ended way using CODAP in the puzzle pieces lesson. And we have scientists regularly come in and talk in our virtual webinars, in our virtual workshops or in-person events. And so we had Megan come in and talk about her process by which she generates questions, plays and explores data, creates new questions that inspire her to go back in the field year after year. And so really wanting to make the connection between teachers, students, like what they're doing in CODAP, the thinking they're doing is what actual scientists are doing. They're exploring these large data sets, they're organizing them, they're asking questions, and they're coming up with answers, but they're coming up with more questions than what they started with. And so pulling this all together, we've got the structured data puzzle lessons. They're following this ambitious science teaching framework where students are making sense of the world around them through their lived experiences and applying that and revising their thinking by applying it to a new science investigation, analyzing some data, making explanatory models, generating new questions, which they can then investigate in these puzzle pieces, these more open-ended investigations where they're the drivers of their learning, and then they're sharing that learning with their peers. Right now, what we're doing, I'm continuing to develop these structured data puzzle lessons and test out these puzzle pieces with schools across the country. We're doing some work related to the polar vortex, but framing it as weather versus climate, just because you experience some extreme cold. What's the winter climate looking like in your area? I used extreme cold weather NFL football game last year between the Kansas City Chiefs and the Miami Dolphins to kind of introduce that, where Patrick Mahomes broke his helmet and Taylor Swift was there, all bundled up. There were something like 20 people hospitalized with frostbite. And so thinking about, it was so cold, that was the fourth coldest NFL game ever, but is that normal for that area? What's winter climate like? And so we didn't really bring in the polar vortex, the fact that it was that cold air mass that prompted that extreme cold, but just an example of the way in which we contextualize some of these big science ideas, and then the way in which we might look for specific data sets to support students making sense of these ideas. Doing some more work with serious scientists who are studying high mountain watersheds in the Rockies. So the big idea there we're exploring is the water cycle, but getting into some more sophisticated applications of the science and technology, thinking more about energy budget, incoming and outgoing energy, as opposed to just like condensation, melting liquid, you know, some of those more simplified things that we might think of the water cycle, but really trying to investigate all parts. And we're making virtual field trips with a number of serious scientists as well. So these are things that we work with serious scientists and scientists nationally. As you saw, Duke, University of Georgia, these scientists might reach out to us if they need help with some outreach or if they're interested in making data puzzles, and we can start that conversation. And we do work with other scientists to produce these virtual field trips as well. So excited to collaborate with anyone and everyone on this work. Much of my time right now is actually developing a research project. We just got funding from an NSF grant. Thankfully, have 2 years in the bank right now. So we know we're going to be doing this for the next couple of years, where we're developing, implementing, and researching a professional learning framework around these data puzzle resources, trying to grow teachers' confidence teaching data skills and with using climate data. So that's what I'm working on now. Very fortunate to get to work on that with folks from DataSpire, who are kind of a private data science group, folks at the University of Tennessee, University of California, Berkeley, which I need to include here, but want to acknowledge NSF's contribution to this presentation and our work moving forward. And that's it. That's the talk. Thanks all. Thanks for your patience with me. Yeah. Any questions? Would love to talk more about this. Yeah.
So CODAP was pretty cool.
CODAP's awesome.
But so how did data get into CODAP? And what do you do if you don't have the data in such a cool platform?
So the question for our online audience is, how does the data get into CODAP, and where do you find that data if you don't have that cool data there? Is there already data there? How do you get your data into CODAP?
Well, what do you do if it's not, like you don't have such a cool platform?
Or what do you do if you don't have this platform?
Great question. So what I've just done, the way CODAP works is you can just drag and drop a CSV file of your data into a window and it'll pop up as a table. So what I've done here, I've just downloaded this data set as a CSV file. You can see it on my window here. We can do this together. I'll go to CODAP, open it up, just launch CODAP over here. I'm going to create a new document, and I'll just drag it over here, and that data set will populate here. So you need to have that data set organized in Excel or Google Sheets, downloaded as a CSV, and then you drag and drop it over. What we do on that site that I was showing you is you can share these and save them in particular ways. Becky and I were talking about this, a really excellent way to differentiate. I talked to my colleagues, what's the right number of variables to give to a 13-year-old. Some people want to push them 5 or 6, maybe you only want 2 or 3 variables. So you could create different CSV files, create different CODAP windows with different links to share and have people investigate different things. So we've done that. These are pre-made here with the data sets and graphs. But yeah, all you've got to do is have your data in a CSV file and you can drag and drop it over. It's what I've started to do now, just like when I get a new data set. It's just a really quick way to play around and get familiar with it and identify relationships if they exist. Yeah?
Just following up, how many roads can it accept? Like you said, you're
Yeah.
The question is, how many rows can CodeApp accept?
So what I learned working with Tyler McIntosh is that you can have like 5,000 points. So I'm not sure what the number of rows is, but we've got, in this particular data puzzle piece, I should say, we chose wildfire data from 2012 to 2020 because that was the max number of points that we could get in there before it started to operate slowly. So this is the biggest data set we have, about 5,000 data points. And I know they're trying to upgrade the software now to make it accommodate more points. But yeah, it started to really operate slowly beyond that. But I think the power of for me, and I think for students, like being able to have the map feature along with, because you can click on the screen here and see where that fire is here. I can highlight parts of the graph and it'll show up on the map. So I'm not privy to all of the things that you can do with CodeApp, but that almost makes it more fun for me to play with. It's kind of a black hole that can take time away from what I should be doing, but I've had a good time learning, and that's what we've heard from students too, just the opportunity to play. Yeah.
I was curious, as you're like working with teachers to implement this stuff, what aspect of these like 4 quadrants is the most challenging to implement for the students, and what aspect is the most challenging to like help the teachers implement?
Yeah.
So the question for our online listeners is that when teachers are implementing these lessons, which quadrant is most challenging for teachers and which is most challenging for students?
I will say that what's most challenging for teachers is this top right quadrant, eliciting students' ideas. It's not in the student worksheet. It takes 20-ish minutes to do, and teachers might not find it, like they might say, I don't have enough time to do that, or might not find it valuable to do that. And so that's what we see is something that's most often skipped. And then when we talk to teachers, they look forward to doing it again so they can incorporate that part, because so much of these data puzzles is relying back on what students already know and their lived experiences. And we challenge the teacher to bring it up multiple times. We challenge students to integrate it, what they already know, to these new science investigations, these new places. So with teachers, I find that that's the part that's most often skipped. And I'm not sure, in your work as well, as we're thinking about communicating with people, right? We want to start with their own lived experience. Shannon, our conversation sticks out hugely this morning. It's like, you know, what are the people of Baltimore thinking about in terms of how they feel about trees? Like, we won't know unless we ask them about their lived experience and how we can build from that. And I think in curriculum and in education, it's so important to start there. For students, they want to know the answer, and they're mad when they aren't told the answer right away. So they've got to come up with a prediction for a question. Just tell me the answer to that question. I don't think that the data parts are familiar with them. I think one part where they get stuck are the explanatory models at the end. Few of them have had to do that before. Like, what do you want me to put here? Like, a lot of times I'll give them a key so that the symbols and the things I want them to include are there. I might give them a background image, and so those starting points might prepare them to be able to construct an explanatory model, and you might take some of those scaffolds away with experienced modelers. But I think students they struggle with not having the answer right away and constructing those models. After some practice, my experience in the middle school classroom is like those are some of their favorite times to be able to be creative and artistic in the way they represent new understandings. And so the modeling piece and those annotated sketches are some of their favorite parts of the lesson, but I would say initially less so. Yeah.
Is there guidance from
questions, are there strategies or guidance for how to adapt these techniques to different age ranges or grades?
No, unfortunately not. There are not. What we've tried to do is on this data puzzle page. So here are the lessons that we have. I think there are something like 15 actual scaffolded data puzzle lessons. We've got some asynchronous workshops, a number of these puzzle pieces. And this instructional framework page is your best bet for that. Basically, a more in-depth description of each of those parts with video footage of teachers enacting those parts in their classroom. And then some individual practice pages where these ambitious science teaching practices are broken out into steps and some more strategies and examples of what it might look like in a classroom are here. So it's not differentiated by grade level, but hopefully the videos and additional context through these resources might spark that. Thanks for that question.
We have a question from our online audience. Can you model using CodeApp? I think they're using modeling in the ecological science version and not the modeling that you're using, that we're using for classroom instruction. Maybe you want to clarify that difference for that question.
The modeling I'm referring to in data puzzle lessons has to do with like annotated sketches, representations of our understanding of the world, maybe even an illustration as a use of a predictive model. If I change this part of the system, how might that impact the model that you've drawn, your annotated sketches? This question might be about computational modeling, using our understanding of physics and math applications to make predictions. And I have not done that with CodeApp, but I think that you can do some. Do you know the answer to that, Becky? Becky and I were just having a conversation this morning about our understandings and learnings of CodeApp. And there are all sorts of, I know there's a tool called Sage Modeler that is embedded in that tool. Is that what you were going to say? Are you privy to that?
So CodeApp was developed by a guy, Dan Downlin, and other folks at Concord Consortium, and they developed Sage Modeler as part of that. I haven't used that aspect of it either, but I think the person who asked the question could contact those folks directly because they're very interested in collaborating with users. So CodeApp is a great partner, and we have an in-house CodeApp aficionado, which is Angie Good, who works for me down in Baltimore, but she's giving a workshop this afternoon that will include an introduction to CodeApp. So if you want to start playing with it and you run into a glitch and you need somebody to talk you through it, Angie's a Carey Institute employee and would be happy to help you with it.
Yeah, thanks for that. And yet, in addition to Angie, you can reach out to me. And like, I don't know how to use Sage Modeler, but I have developed relationships with Dan and others at the Concord Consortium who, like you said, are really excited to work with users. Actually, I was just at a conference with them 2 weeks ago in San Antonio, and they were running lots of CodeApp sessions, attending all sessions just to try to figure out how it's being used. So yeah, like you said, they're excited to answer questions and collaborate.
It's noon. Thank you, everybody, for joining us. If you have more questions for John and you didn't have a sign-up slot, we have an open conversation downstairs in the conference room at 1 o'clock after lunch if you want to continue conversation or pop in to join in our conversation about this big task of translating data to classrooms. And thank you, John, for your time. And there's a happy hour from 4 to 5 this afternoon as another opportunity to interact with John. Thank you so much for your talk.
Yeah, thanks for being here.